Quantum entanglement, a phenomenon in quantum physics, has fascinated scientists and researchers for decades. One of its most promising and impactful applications lies in the field of secure communication, where it can be harnessed to create virtually unbreakable encryption schemes and enable secure communication channels. This concept is at the heart of quantum cryptography, a revolutionary approach to ensuring the confidentiality and integrity of information exchange. Understanding quantum entanglement. Quantum entanglement occurs when two or more particles become correlated in such a way that the properties of one particle instantaneously affect the properties of the other, regardless of the distance between them. This instantaneous interaction seems to defy classical physics and forms the basis of various quantum phenomena. Notably, entanglement provides a unique way to transmit information securely. Quantum key distribution, QKD. Quantum key distribution, QKD, is a key application of quantum entanglement in secure communication. The most famous QKD protocol is the BB84 protocol, proposed by Charles Bennett and Gilles Broussard in 1984. It leverages the principles of quantum mechanics to establish a shared secret key between two parties, commonly referred to as Alice and Bob. This key can then be used for encryption and decryption in a manner that is theoretically invulnerable to eavesdropping. Here's how the BB84 protocol works. Key generation. Alice prepares a sequence of quantum bits, qubits, using a random basis, either horizontal/vertical or diagonal/antidiagonal. She sends these qubits to Bob. Measurement and basis matching. Bob randomly measures each qubit he receives in one of the two bases. However, Alice and Bob's choices of bases for each qubit must match. They keep a record of which qubits were measured in matching bases. Public discussion. Alice and Bob publicly announce the bases they used for each qubit without revealing the actual values of the qubits. Error checking. They compare a subset of their measurements to detect any discrepancies caused by errors or potential eavesdropping. If the error rate is low enough, they proceed. Key distillation. Alice and Bob perform additional operations on their qubit sequence to extract a shorter but secure key. This process involves privacy amplification, which reduces the risk of an eavesdropper having useful information. Shared key. The remaining bits of the qubit sequence form a shared secret key between Alice and Bob. This key can be used for encryption using conventional cryptographic methods. Advantages of quantum entanglement in secure communication. Unconditional security. Quantum key distribution offers a level of security based on the fundamental principles of quantum mechanics. It is immune to traditional cryptographic attacks and the increasing computational power of adversaries. Detection of eavesdropping. Any attempt by an eavesdropper, usually called Eve, to intercept the qubits will disturb their quantum states, causing errors that Alice and Bob can detect during error checking. Perfect secrecy. If implemented correctly, quantum key distribution ensures perfect secrecy in the communication. Even if an eavesdropper has the resources to listen to all communication, they won't be able to gain any information about the shared key. Future-proof. Quantum cryptography is considered future-proof as it's not vulnerable to attacks from quantum computers, which have the potential to break many classical encryption methods. Challenges and considerations. While quantum entanglement holds tremendous promise for secure communication, there are practical challenges. Technical constraints. Building and maintaining quantum communication systems is highly demanding due to the delicate nature of quantum states and the requirement for specialized hardware. Distance limitations. Quantum signals can be easily attenuated and disrupted over long distances. Practical implementations are often constrained by the distance between the communicating parties. Key exchange rate. The rate at which quantum keys can be exchanged is currently limited by the technologies used. This can affect the real-world usability of quantum cryptography. Cost: developing and deploying quantum communication infrastructure can be expensive due to the need for specialized equipment and technologies. Conclusion: quantum entanglement is a cornerstone of quantum cryptography, enabling the creation of secure communication channels that offer unprecedented levels of security. While challenges exist, ongoing research and technological advancements are bringing us closer to practical and scalable quantum communication systems. As quantum technologies continue to evolve, we can expect to see even more innovative applications that harness the power of entanglement for secure communication in an increasingly interconnected world.